Thanks, everyone. This is work that I've been doing with Pascal Garot back in UC Santa Cruz for the past year or so. So there was a nice shout out to double diffusive convection in the last talk. Today I'm going to be specifically talking about one of the two kinds, which is fingering convection, also known as thermohaline mixing. Thermohaline mixing happens in stably stratified regions. So this is a Ledoux stable part of a star. So this is in the radiation zones, not the convection zones, where you have a competing temperature gradient and a chemical composition gradient. Or you can think of, instead of chemical composition, think of that as mean molecular weight, mu. So imagine that we have a stable region. So we have excess heat on the top relative to the bottom, and we have a slight inversion of the mean molecular weight. So overall, it's Ledoux stable. We still have a higher mass density on bottom than at the top. So this is not going to drive overturning convection. So what that means is if you take a parcel of fluid from the top and displace it downwards a little bit, because of the excess heat that this parcel of fluid has, it still wants to buoyantly rise because it has, because it's lighter than its surroundings. But if you note the fact that in these fluids, in stars and in the oceans, thermal diffusion is much faster than chemical diffusion, what that means is before this starts to buoyantly rise, it loses its excess heat and it comes into thermal equilibrium. And now it still has excess mean molecular weight, but it doesn't have the excess heat. It's heavier than its surroundings and it can buoyantly sink. So this is the fingering instability, drives thermohaline mixing. I want to stress that it hinges on these diffusion coefficients being very different and having an inversion of the mean molecular weight gradient. And specifically, it's driven by that gradient. So the destabilizing mechanism is this grad mu, and it's competing against the stabilizing temperature gradient. So you have these two effects working against each other. There's a few examples in stars where this matters a lot. One of them is polluted white dwarfs. There's some work by Evan Bauer and Lars Bildston on noting that if you look at the pollution of white dwarfs and try to infer the mass accretion rate from, say, an accretion disk or something, then if you do take thermohaline mixing into account, because it's so efficient, it tells you that your accretion rate goes through the roof in order to explain the observations if you're going to use a sort of balance like that. Another example that I didn't know about until recently, talking to Ilva, this is related to her fantastic talk yesterday and a previous talk that she gave at this workshop on massive binary systems, where you have a stripped star that's lost its envelope to some accretor star. That accretor star now has regions that are thought to be thermohaline unstable, and that can actually, in some cases, be a very significant mixing process in those stars. An example that I know a little bit more about is red giant branch stars after the first dredge up, so at the luminosity bump or afterwards. There's a lot of anomalous mixing that's seen in lithium depletion or C12, C13, C over N, where basically there's depletion of surface abundances that can't be explained by standard stellar models, and you need some sort of mixing mechanism below the convection zone. There's a really great paper recently that I think does a lot of other things in the paper, but it also goes into detail about this, what's going on here. What drives the mixing? I'm going to say it's thermohaline mixing because that's what I'm here to talk about. All right, a little bit more about that RGB star problem. There are a lot of papers about it that I'm not citing here, so I apologize if to people who might be listening. But this is just sort of the overview as it pertains to this talk. So in 2010 and 2013, Decay and collaborators added thermohaline mixing to MESA. And you can see the results of this here. This is taken from that MESA paper up there, I think. This is when thermohaline mixing kicks in these red giant branch stars. So this is a Kippenhahn diagram. So we basically got, this is the mass coordinate here. You can think of that as radius. And along here is model number. You can think of that as time. You can see here the convective envelope dips up or dips down in the dredge up event. And then after dredge up, this region is chemically mixed by this convection zone being down here. As the hydrogen-bearing shell is expanding outwards, it eventually reaches into this region that was chemically mixed. Now, if you don't have thermohaline mixing turned on, there's nothing to allow chemicals to mix between this convective envelope and the hydrogen-bearing shell. But thermohaline mixing, if it's efficient enough, can allow significant mixing of chemical species down to the hydrogen-bearing shell, and thus explain, say, lithium depletion. Now, in this work, they used what's currently implemented in MESA as called the Kippenhahn model, I'm pretty sure. And that model includes free parameters that basically tune the efficiency of thermohaline mixing because it wasn't well constrained at the time. And they found that depending on how you tune those parameters, you can either agree with observations or you don't because it's not efficient enough. At the same time, some work was done on the hydro side, doing some 3D hydro simulations where it was found that basically simulations don't predict mixing that's efficient enough to match up with observations. So that's a problem. The efficiencies that were used in that work don't match up with hydro simulations. It's a shame. A lot of other work was done, and then in 2019, this really nice paper by Harrington and Garreau found that if you add magnetic fields, it does enhance thermohaline mixing dramatically, and it can solve this problem with like pretty standard magnetic field strengths, nothing exotic. So that sort of sets the stage for the rest of this talk. I want to briefly state what simulations we're doing for the fluid dynamicists in the audience, but I'm going to zoom through this because it's not the focus of this talk. We do Gusenesque simulations, so we are ignoring sound waves. These are local models. We're zooming into a very, very small region of the star where the pressure scale height is, through the roof. Very, very small boxes. We can linearize everything, at least the equation of state. So we linearize the equation of state. So density perturbations are linear in temperature fluctuations and chemical composition fluctuations. And we look at local models. So those of you familiar with shearing box models, it's kind of the same deal, where we've got fixed background gradients of temperature and composition, and we look at fluctuations on top of that that are triply periodic, so we can use a pseudospectral code. Our non-dimensionalization, basically our length scale is non-dimensionalized in terms of what dimensional analysis tells you the width of these fingers should be. So that means that a width of 1 in our units is like what you think the width of these fingers should be. Ends up being a bit bigger than that. And then the flow speed, or equivalently the time scale, is given by thermal diffusion. These are the equations we're solving. If you're not familiar with this stuff, that's fine, but it's the Gusenesque equations. And we've got advection diffusion equations for T and C. This term here and this term here, that's just advection of the background gradient. The thing that is important to note is the free parameters that we have in these simulations. The Prandtl number is the ratio of the viscous diffusion coefficient to the thermal diffusion coefficient. This tau is the ratio of the compositional and thermal diffusion coefficients. Remember I said that that has to be far from 1, or at least not equal to 1, in order for this instability to act. These two quantities in stars are close enough to being equal, and they're like 10 to the minus 6 in some of the stars that we care about. That's really hard to simulate, as in like you can't simulate that. The best simulations we can do go down to Prandtl number of 10 to the minus 1, 10 to the minus 2. So the name of the game is to come up with a mixing prescription that agrees with simulations at accessible Prandtl numbers, and then extrapolate it to, what happens in stars. R naught here is called the density ratio. Remember I said that this instability is sort of between a destabilizing composition gradient and a stabilizing temperature gradient, and this just parameterizes the two, the ratio of the two. If R naught is large, then the stabilizing temperature gradient wins. If it's small, then you've got this destabilizing composition gradient. So the instability acts whenever R naught is between 1 and 1 over tau, so it has to be greater than 1. Now, the goal in tau, the name of the game is predict mixing as a function of these free parameters, because then you can plug that into MESA and run with it. The way that we're going to parameterize mixing is in terms of what's known as the Nusselt number. It's the total flux divided by the diffusive flux. What you can think of it as, it's not exactly this, is that your turbulent diffusivity is going to be your Nusselt number times your molecular diffusivity in a hand-wavy sense. So if your Nusselt number is 10, that means that your turbulent mixing is 10 times efficient as your molecular diffusion.
Sorry, Adrian. Quick comment from Pascal noting that in some thin regimes, you can get down to Prandtl numbers of 10 to minus 3.
That's right. Good point. Thank you. I think I have a figure from one of her papers in here where she did do 10 to the minus 3, so I should have caught that. All right, so we're working with MHD where we add a magnetic field. And so the important differences are highlighted in red here. I just want to focus on the fact that we've got a Lorentz force now in the momentum equation. And And the coefficient in front of the Lorentz force here, HB, is just measuring the strength of the magnetic field that we impose on our simulations. So all the simulations I'm talking about today, we've got these Booson-esque boxes of thermohaline mixing, and we have uniform vertical magnetic fields threading the box for our initial condition. And HB just measures the squared amplitude of that initial magnetic field strength. So I'm going to show plots where HB is varying, and that just means that the imposed magnetic field is changing. So I called this talk Problems with Parasites because parasitic saturation models turns out has problems, and that matters for other instabilities as well, where these models are used, such as GSF and MRI. Before I go into the details of what these parasitic saturation models are, I just want to show you how well they can work. For example, in thermohaline mixing and hydro. So this is what's implemented, I believe, in MESA as the Brown et al. Model, or Brown 13, something like that, and it's great. You should use it. So this is a plot of Nusselt number, so mixing efficiency versus R naught density ratio. Comparing in points, this is simulations, and then the curve is this Brown et al. Model. And you can see that as far as any of us really care, it's bang on. It does a great job. Now, this model has two key ingredients that I want to highlight. They both come from looking closely at simulations. You can sort of see the merit of these ingredients. Here I'm showing a simulation of thermohaline mixing very, very early on, before turbulence has set in, where you just have exponential growth of the instability. The fastest growing modes that emerge in the linear growth regime are the so-called elevator modes. So what I'm plotting here is the vertical velocity at this point in the simulation. Red here is an upward moving flow. Blue here is a downward moving flow. This is carrying the gradients of mean molecular weight and doing the mixing. And you can see why they're called elevators. They're growing like e to the lambda t, where lambda is the growth rate of the finger instability. Because they're the fastest growing modes, and because we have to make assumptions somewhere in order to make good models, we're going to assume that they dominate the mixing. And so if you can figure out the amplitude of these elevator modes, that gets you the mixing efficiency. So mixing is going to be proportional to the elevator amplitude really squared. There should be a factor, WF squared. The second ingredient comes from the next step in these simulations. So these elevator modes are shear flows. So you have this upward moving flow here and not here, that's the shear layer. That shear flow is growing exponentially in time, right? That e to the lambda t. As it grows, it's going to eventually drive a KH instability. For those of you familiar with KH, you know that the growth rate of KH instability depends on the amplitude of the shear flow. So let's see, e to the sigma t. Sigma here is the growth rate of the KH instability. Sigma is going to be a function of the amplitude of the shear flow. We're going to assume that in saturation, these two timescales are in balance. So the growth of the fingers through the finger instability is going to be balanced by their disruption by a KH. So sigma is equal to lambda with some constant of order unity that you can fit. Because sigma depends on the amplitude of the fingers, you can invert this expression to get the finger amplitude. So this assumption gets you the finger amplitude, and then that first ingredient gets you the mixing efficiency. Boom, you're done. This assumption is great. I've looked at this in all of my simulations, and I have no concerns about this. And if this time, I hope to get into the fact that this thing seems troubling. This is also works pretty well in MHD, and these sorts of pictures, I think, show you why magnetic fields enhance mixing efficiency. It basically comes from the fact that magnetic fields reduce the growth rate of the KH instability, and so the finger velocity needs to increase to compensate for that. So because magnetic fields reduce KH growth rate, you still need sigma KH to balance lambda, so velocity needs to increase, and so mixing goes up. This was shown to agree really nicely with models. So this Harrington and Garreau paper in 2019 looked at a set of parameters here, and then they changed the magnetic field strength, and you can see that the model here in black, that parasite model, agrees really nicely with simulations at a bunch of different magnetic field strengths. And this is kind of exciting. At the last minute, I added a couple of slides inspired by Jen's great talk yesterday about where she mentioned smoking guns. There's a couple smoking guns that you can use these models to predict. I'm running out of time, so I'm not going to go into too much detail, but a lot of work's been done by Pascal's group showing that in the right parameter regimes, if you have thermohaline mixing, just like uniform homogeneous turbulence, if the regime is right and the conditions are right, it can excite gravity waves. It can excite convective layers. It can do a lot of really cool stuff that could have observational consequences. Turns out that in hydro, at low Prandtl numbers, like what you find in stars, it's just not efficient enough to drive those mechanisms. That's one of the punchlines of this paper here. But in MHD, mixing efficiency goes up, and suddenly it might be efficient enough to drive these mechanisms. In particular, if you take that Harrington model and run with it, you can get some exciting predictions here that depend on the magnetic field strength being sort of in this Goldilocks regime, not too weak, not too strong. Okay, but it turns out that model has problems. So here I'm showing again Newton number versus R naught. Black is hydro as before, but the curves are different magnetic field strengths. You can see that, so these are models, and then the points are simulations. You see that they don't line up, especially when you go to magnetic Prandtl number less than 1. We've done a lot of work to try to fix this up. It's gotten a little bit better, but there's still a lot of work left to be done. And I don't want to like minimize the amount of work that, like, this is a hard problem. It turns out that it's pretty hard to deal with. Thank you. So we've made some slight improvements, and we're doing a lot of work to improve these models because there are exciting consequences, you know, if you take these models and run with them to stellar parameters. But before we, you know, ring the alarm bells about these exciting smoking guns, we first want to know that we can trust these models. And I said before, there's those 2 key ingredients, and the long story short is that that second one that is used as well in like MRI and GSF that we really have problems with. So I did, you know, 20-minute talk. I don't want to go into too much detail about that side of the problem, what the problems are, what we're doing to fix it. But I want to talk about the key takeaways here. The first is that MHD enhances mixing, and it might enable some of these smoking guns, which would be really cool to see. In particular, the chemical homogenization in those regions, or if there's maybe astroseismology can help us to observe these internal gravity waves. I've been talking to Lisa Bounier about that. That'd be pretty cool. The model unfortunately fails at low magnetic Prandtl number, but there's some work going on to fix it. And so look out for work by Amy Cresswell and Pascal and I on trying to understand the KH saturation physics of those weird shear flows. Proper accounting of the Maxwell stress, this is something that Pascal's been leading that might be the key to this problem, or some work on non-modal growth that I talked about at Bring a Plot earlier. I'll end there. Thank you all.
Okay, questions for Adrian? This is Janos Stuberry. Thank you for the talk. It was really interesting. Have you considered different angles of your magnetic fields with respect to the composition gradients, and how does that change things?
That's a good question. I have not, but this previous paper did. So I should have stressed that we start with the uniform vertical magnetic field because you got to start somewhere, and it turns out that that one's a little bit easier to model as far as what we've tried. This paper did try inclined magnetic fields and I think horizontal fields, at least in Harrington's thesis. It's complicated. From what I remember, those simulations didn't reach a quasi-stationary state, and so where do you go from there? You know, there's follow-up work that needs to be done there. But we're starting with the uniform case and trying to understand it, and then that'll be follow-up.
Yeah, of course. Right, thank you.
Hi, this is Jim Fuller. So I have a question about these elevator modes. If I understand correctly, they're an artifact of your periodic boundary conditions. The real system isn't periodic and so can't have exactly this kind of mode. Do you have any concerns that, you know, a real system saturation of those modes would look different, and so the saturation of the instability in the mixing would look different?
Yeah, that's an important question. I appreciate it. The thing that probably, I mean, that is a concern, but that's why you want to make sure your box size is big enough that the turbulent correlation length in the actual turbulent state, you know, fits within your box, and your final answer doesn't depend on your box size. And that is satisfied. So that's, I should have stressed it when I showed this figure, but you know, if you, once you look past the initial state and at the, you know, fully developed turbulence, our simulations do have a big enough box that as you crank up the box size, mixing doesn't change, and it's independent of the box size. You know, I've been talking a lot with Adam and Evan about, you know, is there merit in even so, like looking at what happens if you actually have a global profile and you have non-periodic boxes. So maybe we can chat more later about that. But I think that the really key answer for now is this doesn't happen in really Bernard convection, right? If you have homogeneous really Bernard convection, you always have the elevator modes. But at least here, we can make the box big enough that it's at least independent of box size.
Hi, I was wondering if you have, oh, hi, I'm Jana Bibiv. I'm actually an oceanographer from a different conference. I was just wondering if you have the lateral gradients in your initial system, or is just all about sort of vertical gradient in temperature and composition?
That's a really good question. We haven't looked. I think that Pascal's group has a previous paper on lateral gradients at low Prandtl number. Please tell me if I'm wrong, Pascal. And you know, I understand that is an important problem. We're just looking at vertical gradients for now.
This is Mathieu. Can you say something about the magnetic field amplitudes that you assume and how they compare with what is expected in various stellar situations?
Yeah, so we parameterize the magnetic field in terms of HB. That's sort of the coefficient that comes out in our non-dimensionalization. And it ends up depending on, you know, so HB is like the Alfvén speed divided by this characteristic U scale squared, which has in it, oh, where'd it go? It has in it, you know, a bunch of other parameters. And so translating from HB to an actual magnetic field strength is non-trivial. You can do it once you like focus on an individual star. And so, for example, in RGB stars, as I recall, the magnetic fields such that this stuff becomes very, very important. It's like on the order of 100 Gauss. Matteo, is that roughly right? Yeah. But it's going to depend on the star. Different stars will have basically different denominators for this, and so I can't give you a simple answer.
So just quick thing in response to the horizontal gradient, and also very happy to see some participation from the other program as well. Pascal notes that it's a paper by Medrano et al. That discusses that.
Hi, this is Valentin Skudnev. It's a clarifying question. Why does the turbulence reach a quasi-stationary state and not like decay once the chemicals have mixed? So why? Maybe I missed something in the setup.
Yeah, that's a good question.
Kind of like a Rayleigh-Taylor saturation or something.
So thank you. That's a good question, and I shouldn't have skipped over this so fast. It's basically because of the model we're using, we have fixed background gradients of the temperature profile and the composition profile. And that's where the free energy is coming from, is from this inversion of the mean molecular weight. And that's fixed. The turbulence never, we don't have quasi-linear flattening, we don't have profile relaxation. So the driving gradient is always turned on. It's kind of like having a local shearing box model of the MRI, you always have that shear profile. Does that make sense?
You're assuming that the regeneration of the chemical gradient is faster than the mixing?
Yeah, there's sort of a timescale argument going on, I guess. Yeah, well, I mean, if you can parameterize mixing efficiency as a function of like imposed gradients, then you can start to ask questions about like timescales, I think, and do a more careful analysis that's getting at your question.
Right. Does the gradient get washed out, right?
Sorry?
Does the gradient get washed out?
Yeah.
And then...
So I think like that is an important question, and I think that that's like an important thing to keep asking with this kind of work. I guess that's what I can say about that. It's like, yeah, we lock in the composition gradient,
okay.
And that's maybe a good reason for Evan and I and Adam to work on a similar problem.
Right, cool, thank you.
So I have a question that's kind of out of left field. So you mentioned the potential for like smoking guns and actually observing signatures of this, including like gravity waves. How would we be able to distinguish thermohaline gravity waves from something like convectively excited gravity waves or any other ones?
Yeah, that's a really good question. I guess it would come from the frequency and maybe the amplitude. I kind of put this in there as a quick, like, hey, look at this cool thing that could happen. And that's an important question to ask that I don't know the answer to. I'm sorry.
A comment from Pascal regarding the previous question, or I guess, Pascal, do you want to address that and also the gravity waves?
You go for it.
Yeah, sorry, I don't want to jump in with a voice without a face. That's why I don't comment. But in terms of, to answer Valentine's question about what would happen if the composition was allowed to evolve freely, we actually tested that in a paper with Varvar Zemskova, Matthew Deal, and Sylvie Vauclair, where we looked at the effect of fingering convection on the concentration of radiatively levitated chemical elements in the surface of A-type stars. And in this case, there was a profile of chemical concentration that was driven by the radiative levitation and then drove these fingering instabilities. And so we did the 3D DNS of that process and compared them with the 1D model of the Brown et al. Prescription, and it was quite remarkable how well the two fit. And in this system, indeed, the compositional profile was evolving self-consistently. So that's for that. And in terms of the question from Evan, I love that question because when we wrote that paper, we were so excited about the possibility of driving gravity waves in a different way. And I think the reason it's not going to work is twofold. The first is the region of parameter space where you get these gravity waves is quite limited. And you need Prandtl numbers that are relatively high, like 10 to the -3-ish. And that is not really common in stellar interiors. The second thing is the scale of these gravity waves is quite small compared with convectively driven gravity waves or otherwise driven gravity waves. They are maybe 100 times larger than a finger, or at most, at least from what the model predictions say. So these are pretty small scale, and then they have an aspect ratio that is very much inclined at a 45-degree angle with respect to the horizontal, whereas otherwise other gravity waves tend to have a much flatter aspect ratio. But because they're so small, I don't think we would ever see them unless something happened to then have an inverse cascade of some sort to drive them to larger scales.
Cool, thank you. Any other questions? I actually do have one more quick one. So you mentioned that you've been doing follow-up work on like MHD KH within the Crestwell. Is that looking good for this assumption that the growth rate of oh my God, I'm forgetting what things are. Basically, assumption 2, is it looking good for that or not?
Yeah, basically, no. That's a good question. So basically, this assumption is saying, oh, well, if you know the growth rate of KH and you know the growth rate of the finger instability, that's all you really need in order to figure out what the amplitude of the finger is going to be. And Emmy's got a bunch of really cool simulations. Basically, because the alpha and Mach number of these flows is so low, I mean, so close to being, at the threshold, and because the magnetic Reynolds number ends up being so low in these primary regions that we're looking at, that assumption should go out the window. It seems to be set by totally different things. So look forward to future work on that.
Okay, let's thank Adrian again for a great talk.